Hello and welcome to the webinar on Pathmind Reinforcement Learning for Simulation. My name is Arash Mahdavi and I'm your host today. Today, as our guest presenters, we are thrilled to have Edward Jumprang and Sahar Esmailzadeh. Edward is Head of Customer Success at Pathmind. He works to introduce benefits of reinforcement learning for simulation to organizations who are looking to improve their optimization strategies and helps new users navigate the process of implementing AI in their simulations. Sahar Esmailzadeh is lead simulation engineer at Pathmind, where she collaborates with organizations to adapt their simulations for success with reinforcement learning and models new business problems to demonstrate the power of AI as an optimization tool. Sahar holds a master's degree in industrial engineering. In this webinar, Edward and Sahar will introduce you to the capabilities of reinforcement learning, demonstrate how to set up an AnyLogic model for RL and train it in Pathmind web application, and we will also showcase the impact of RL on simulation performance. They will also examine two simulation models that demonstrate the type of success being seen by Pathmind users across various industries. During this webinar, I try to put myself in the audience's shoes, asking questions that might clarify or expand on some of the topics discussed. As mentioned, we will come back at the end for the live Q&A section to answer your questions. Asking questions early will give you the best chance of getting an answer. Without further ado, let's start the webinar.
Hi, my name is Edward, and I handle customer success at Pathmind.
Hi, I'm Sahar. I'm the lead simulation engineer at Pathmind.
In today's webinar, we will provide an overview of Pathmind, a comparison of heuristics, optimizers, and reinforcement learning, when and why you should consider reinforcement learning, and finally a walkthrough of two examples, an HPV example and a multi-echelon product delivery example. So just to start with, what is Pathmind? Think of Pathmind as a bridge between AnyLogic, which is the stuff on the left, and the reinforcement learning ecosystem, which is the stuff on the right. Pathmind is a software as a service tool that enables you to train a reinforcement learning policy using your existing AnyLogic simulation. Our goal is to make it easy for industrial engineers who typically don't have a data science or software engineering background to leverage reinforcement learning. All you need is to focus on your real-world simulation built using AnyLogic, and Pathmind will handle the rest. So how it works, Pathmind operates in 2 steps. So step 1 is to configure reinforcement learning directly inside your AnyLogic simulation. It's in the form of a custom palette item that you can download and add to AnyLogic. This palette item exposes fields necessary to train a reinforcement learning policy. So you can essentially set everything up the AnyLogic way. There's no need to learn a new paradigm to use reinforcement learning. So step 2, so after finishing step 1, simply import your simulation to Pathmind using AnyLogic's RL experiment. From there, you'll be prompted to write a reward function, which we'll explain later, and then simply click the train button. Pathmind will handle the rest automatically. There's no data science experience required. Okay, so now here's how Pathmind fits into an industrial engineering workflow. At the top, you can see a simplified workflow illustrating how simulation can be used to optimize real-world use cases. This is your simulation environment, and it is your vehicle for exploring scenarios with the goal of improving business outcomes. So using simulation as a vehicle, you can optimize your simulation in 3 ways. So the most common approach from what I've seen at least is to apply a heuristic, which is basically a set of static rules. So these rules tell a system how to react to certain situations. The second approach is to apply an optimizer, such as OpQuest. And finally, there's reinforcement learning, which has only recently grown in popularity. So I put an image of a neural network here because it's kind of like a black box. So the commonality of all three of these approaches is that they utilize a similar kind of feedback loop in which you observe your environment, you make a decision or take an action, and then you evaluate the outcome. So that's why reinforcement learning kind of fits nicely in a typical industrial engineering workflow. And you can kind of say that industrial engineers have been doing reinforcement learning manually for decades. Okay, so just to dig deeper into each approach, as I mentioned in the previous slide, heuristics are probably the most widely used optimization tactic from what I've seen because they're easy to understand and they're easy to implement. When implementing a heuristic in practice, a factory manager, for example, can easily understand what is going on, which makes buy-in a lot easier. However, the problem is that heuristics are not scalable. They can grow to hundreds of lines of code, and they're inherently inflexible in nature. So if anything changes, you'll have to retroactively adjust your heuristic, which can be a pain, especially if your heuristic is very complicated. So on the right, I put an example of a relatively complex heuristic, and as you can see, it's kind of pretty scary to look at. And if you can imagine updating this, it'd probably be a huge pain. So next is optimizers. And before I talk about optimizers, I just want to say that I'm not an expert. I've only used OpQuest, so feel free to be skeptical of any of my assertions here. Anyways, to somewhat address the limitation of heuristics and to leverage the abundance of compute nowadays, I've seen many industrial engineers take advantage of optimizers. So mechanically, an optimizer, and again, I've only used OpQuest, will replay the simulation over and over again until it finds the best set of parameters that maximizes or minimizes a metric that you care about. So I would say it's almost kind of like brute forcing a solution. So they're relatively easy to set up. It's not a black box, so you know how it found a solution. The disadvantages is that they must be rerun frequently. They're computationally expensive, so it takes a long time to run, and they sometimes aren't able to find a solution. So because of these limitations, it might limit their use in practice. Okay, so finally, there's reinforcement learning, which is kind of takes the best of both worlds, right? So the best of a heuristic, which are essentially learned rules, and optimizers, which automate the discovery process. So you should only consider reinforcement learning if your use case contains these three characteristics. So the first is high variability. So variability means something like a supply chain in which demand can be unpredictable, right? The second is a large state space, which are use cases in which the possible set of outcomes is unconstrained and infinitely large. So if you were to think of like a robotic arm, for example, it has freedom of movement in 3D space. So the number of possible decisions you can make is massive. So imagine running a heuristic for a robotic arm that accommodates every scenario. It would be nearly impossible. And finally, multiple contradictory objectives. So an example of this could be a factory that wants to reduce costs while also maximizing throughput. If you were to ask an optimizer to reduce costs in this case, a reasonable solution could be to simply shut down production, so cost is zero. But reinforcement learning is flexible enough to avoid those type of outcomes. As for cons, I would say that many organizations hesitate to use reinforcement learning because data scientists are hard to come by, and reinforcement learning operates like a black box. It's hard to know why a certain outcome was made, why a certain decision was made, and you can't really tell a factory manager that you don't know why a reinforcement learning policy recommended a particular action. Right? They would just freak out. So I wanted to quickly go over a couple examples that we have applied to reinforcement learning to. Most of these are already in AnyLogic Cloud, so you can take a look later. These range from assembly lines, routing AGVs to production scheduling. And the green rectangles there are what we found to be reinforcement learning's improvement over a heuristic or an optimizer. And in this case, we always use OpQuest. I won't go into detail, but these use cases share the same characteristics that I mentioned in the previous slide, which are high variability, complex state spaces, and contradictory objectives. So that's kind of like how we identify these as promising use cases for reinforcement learning. So before I proceed, I just want to say that reinforcement learning is not better or worse than a heuristic or optimizer. We've encountered use cases in which reinforcement learning can't even beat a simple heuristic and vice versa. It's just another option that you can try out. Okay, so finally, I just wanted to address what you can do with the train policy. Basically like so what? How does reinforcement learning materialize in real life? From our experience, we have seen users use reinforcement learning in two ways. Some have used reinforcement learning to derive a better heuristic by studying the policy's behavior. Presenting management with a reinforcement learning enhanced heuristic is a lot easier than giving them a black box. And I can say with confidence that nobody wants a black box, right? And secondly, others have deployed a reinforcement learning policy directly and compared it side by side with a heuristic and optimizer. From there, they allow the human operator to decide which approach to follow. And just to mention quickly, for directly deploying a policy, you can do so in two ways with Pathmind. You can download the actual policy file and query it yourself. This might be beneficial if there are any security or performance concerns in your organization. Or you can use Pathmind's policy server, in which we basically wire everything up for you, right? And just query the REST endpoint. We'll probably dig deeper into policy serving in a subsequent webinar. Yeah, so to use Pathmind, first add a new RL experiment. So right click here, experiment, RL experiment. Now, once you add RL experiment, Pathmind will show up as an option inside the properties view. So everything in here, observations, actions, etc., you can ignore completely. You would just use RL experiment to simply export your simulation into Pathmind. And the point of this is that it enables you to utilize Pathmind even if you're on AnyLogic PLE. So once you have your RL experiment added to your model, you can go into Pathmind Helper to set up the fields related to reinforcement learning. The first thing I want to show, basically the first step to use Pathmind is to install the Pathmind Helper. So you can go pathmind.com and go to our help docs, and there'll be a page to download the Pathmind Helper. So it'll be in the form of this jar file here. Once you download it, you go back into AnyLogic, click this button on the top left, the bottom left, manage libraries, and then you can add custom libraries into AnyLogic using this option. So you click add, you find the Pathmind helper file that you just downloaded, and then click OK. And once you add that, you'll see Pathmind appear as a palette item that you can drag and drop into your AnyLogic simulation. So I have a pre-configured one right here that you guys can take a look at. So basically what Pathmind Helper does is that it exposes fields related to reinforcement learning directly in your AnyLogic simulation. So just to quickly go over them, you have your observations, which basically express the state of your environment, right? Metrics, which are also known as rewards. These are KPIs that tell the policy whether or not it's doing a good job. And then actions, which this is probably the most complicated field, but they're basically, you define all the possible actions that are available to a policy. And then finally, these are event triggers. Event triggers are the frequency in which a policy makes a decision. So this could be on a fixed recurring basis, or it could be triggered dynamically inside your simulation, like for example, inside your process logic. I won't go into the other fields in this webinar because they're a little more complex. But I can say that Pathmind pretty much supports everything in the RL ecosystem, such as multiple agents, tuple actions, action mass. So all these are all supported within this interface here that you see on the screen. So once you're finished setting up these fields, simply run your simulation with debug mode turned on, and you can kind of see how these fields materialize in your AnyLogic model. Yeah, so as you can see on the right, every time an event is triggered, it triggers a step. And inside each step, you can see the observations, metrics, and actions that you had defined. So essentially how this chain works is the policy will see the observations, it'll take an action, and then it'll evaluate how good the action was using the metrics. So this is kind of like the cycle that the policy takes in order to learn how to optimize a certain outcome. So once that's done, so once you confirm that your model works as expected.
What you showed was run locally, right? So you are not using Pathmind at this point. You're testing the simulation and the configuration on your machine before you uploading it, right?
Mm-hmm. That's right.
And the experiment that you ran was the simulation experiment, not the RL experiment.
Mm-hmm. That's correct.
Okay, yep. Thank
you. Once you confirm that everything is correct, go back to RL experiment and you click export to Pathmind. And once inside here, you'll be prompted to submit an access token, which I'll show you where to find that after this. And then once you click next, it will begin importing your simulation to Pathmind. Yeah, so once your RL experiment is finished uploading, so it takes like 5 to 10 minutes, AnyLogic will open up the Pathmind web application. So if I jump over here, so when the upload is done and the web application is opened, the first thing you'll see is this page here that prompts you to write a reward function. And the reward function, we'll go into more detail during Sahar's demo, but a reward function basically tells the policy what's good and what's bad, right? So once you provide a reward function, you click the train button. After you click the train button, and I will jump to an experiment that's already been trained, you'll be presented with these graphs that show you how well the policy had learned, right? Once this is done, you click export policy. So it'll be the form of a zip file. So this is the train policy. You save this file, and then you go back to AnyLogic and load the file in your simulation. So when you go back to AnyLogic, you click on Pathmind Helper. Where it says mode, you change that to use policy, and then you point it to the policy file that you just downloaded in Pathmind. And from there, you can validate what your policy had learned. So that's like the high-level workflow. So I think I'm going to pass it to Sahar now, who will go over the multi-echelon product delivery model.
This is multi-echelon product delivery model. In this model, we have 2 manufacturers, 4 distributors, and 8 retailers. Manufacturers produce products with a certain rate. They do a semi-finished products, then they give it to distributor. Distributor with certain capacity also does more assembly on the product, so there is a lead time on the distributor too. Then a retailer can buy those products and hand it to the customers. The base logic uses a hybrid of nearest neighbor plus an optimization of RQ, which is basically little s big S optimization. So at each step, each of the locations or nodes always order from their nearest supplier, and they order until the amount they order is to replenish to the target that optimizer has set, plus any backlog if they have. Now going back and running with policy. So policy at each day dynamically chooses where to order from and how much to order it. Pathmind policy in this model beats heuristic optimizer by about 30%. I'll now go back in the model and show you the fields for RL. So in this model, observations include the stock level, backlog, and expected order for all of the locations. So for all of the distributors, retailers, and manufacturers, and also includes time of the day, time of the week, and a time of a day of the year. This is because demand pattern kind of follows a weekly and seasonal fluctuation. So, for example, in middle of the week, you can expect higher demand than end of the week, and also in some seasons, the demand is in general higher. So we are giving the time to the policy so it can predict what to expect as a demand. As for metrics, we have included many. You can see all these metrics back in Pathmind webapp when you upload your model. So you can see how these metrics evolve as the RL agent trains. For training this specific policy, we have basically just used the profit, so maximize that. And we have used minimizing queued orders. As for actions, it's a mixed tuple. It selects a manufacturer, amount to order, it selects a distributor, and amount to order. So this is a single agent setup. So RL is kind of acting as a control tower, coordinating and deciding for all of the locations. And the triggers are every day.
Okay, Sahar, can you tell me what is the difference between the observations and metrics, or can be any overlap between what is observed and what the metrics are?
So typically as observation, we include all the informations that are necessary to make an informed decision. That could include, so for example, here we have the queued orders are part of the observation, and also it includes in the metrics. So metrics is it could be used as our objective. So you give reward or punishment to the agent based on their metric. Metrics, if they are used in the reward function, are much stronger signal, and it is what the RL agent strives for, rather than observations, which RL agent tries to make sense of it and find connections between the reward that it gets and the observations that it has seen.
Can you please walk us through, for example, what at discrete n equals to size for 4, and how can I interpret the syntax?
Let's look at the first decision. So it selects a manufacturer. It's a discrete decision with n equals 2, meaning it can be, as you remember, we have 2 manufacturers. So it can choose either manufacturer 0 or manufacturer 1. So it chooses one of those, but for size 4, meaning that array is of size 4. 4 because we have 4 distributors. So for each of these distributors decides which manufacturer, manufacturer 0 or 1 to order from. Next one is the order amount, which here is, again, is a discrete decision. It can be between 0 and 19. And in the logic, we have set it so that it is stepping by 100. So it is 0, 100, 200, so forth. And again, this is the amount that we have 4 distributors. RL is deciding 4 times how much to order.
Okay, so the last question. So I see that in the event trigger section, you didn't check the Pathmind event trigger. So how did you trigger these events in this model?
Whenever, every day, when the demand is generated, it takes a step. And in this step, it triggers Pathmind. And when it triggers Pathmind, so basically it is just daily triggers. When Pathmind is triggered, it goes through observations and then decides an action. After you upload your model to Pathmind web app, you will see a page much like this that you can see the metrics you have set up in your Pathmind helper. And here you can set a goal for the metrics. So for example, we can say maximize profit. Queues, we don't like queues, so minimize them. And easy as that, if you click next, a simple reward function will be generated for you. And here you can see the observations that you have set back in your AnyLogic model. Yeah, all is ready, no errors. Train the policy. I will not go through reward shaping here since Edward will be doing that for the next example. However, I will show you a finished experiment for multi-echelon product delivery. And as you see, reward starts, and the start is fairly random actions. And as it goes through training, it converges and maximizes a reward function that we have set for it. I will run the model with the optimizer. As you see, the connections are fixed. So it's always just using, always ordering from the same supplier. And the amount that it decides is always replenishing to the target that the optimizer has set. That logic forms 2 clusters of manufacturers, distributors, and retailers. This manufacturer is of higher capacity, so it produces with higher rate. And as you see, this cluster is doing well, and it is not losing much of the demand. But in contrast, this cluster, which all of them are depending on this manufacturer, which has a lower rate, are losing more of the demand. This circle, you can see that the red part of the pie chart is the lost demand. On the other hand, when I run it with Pathmind policy, you will see that policy is dynamically choosing where to order based on the observations that it receives. This distributor here is alternating between which manufacturer it is ordering from. So if the stock of one of the manufacturers is higher, it is gonna dynamically choose that manufacturer.
Sahar, is my understanding correct that the reason behind RL beating that static optimized scenario was that RL is more dynamic? It can adaptively change its setup based on what it sees happening at that moment, or basically results in dealing with variation in a more adaptive way? Is there anything that I'm missing here that might contribute to this better result?
No, exactly what you were saying. It's a big part of why RL is able to outperform the static rules. It is choosing where to order based on the current state of the system. Also, one big factor is that it is coordinating very well between the locations. For example, 2 distributors at the same time place a big order from one of the manufacturers. Of course, that one manufacturer will not be able to respond properly. But as you see, the distributors are alternating between the manufacturers and taking turns and making it in a way that they have less queued orders, because that is what we have used in the reward, so that they are not allowing the orders to pile up. So very agile. Next, there are much more behavioral observations that we can get from the running Monte Carlo. So I will just run the Monte Carlo and show you here the comparison between results of the policy, which is the orange, versus optimizer heuristic hybrid, which is the purple color. Here you see the total profit. Pathmind is 7,400,000. Optimizer is 5.5. If you look at total revenue, you can see Pathmind is having higher revenue than baseline, which you can see also that Pathmind has much less lost demand. It explains why the revenue is higher. But if you look at the costs, you can see that the costs are almost the same amount. If you look at the breakdown of the costs, so transportation costs and inventory costs, we can see that the Pathmind has much higher transportation costs compared to inventory costs. That is, Pathmind has less inventory costs. So what this tells us is that optimizer is having much higher safety stock, it piles up on the inventory in hope that it is gonna respond to the demand that it may or may not get. But Pathmind is much more proactive. It predicts what demand it might get and only orders as much as that. So it holds less inventory, but also in the same time, it takes the advantage of having dynamic flexibility of choosing where to order. So it might order from further places, but it doesn't pile up the inventory either. In the next page, you will see that Pathmind is placing more orders, both for the distributor and retailers, but it does it in lesser quantity. So it only orders as much as it thinks that it needs, and it doesn't clunk up the system by bigger orders and queued up demand.
The way you made these dashboards or presentations was to put back the trained policy into AnyLogic, and those are the orange ones that you ran several times in a Monte Carlo experiment versus what the optimizer heuristic hybrid does in a Monte Carlo simulation. So you see the comparison between Monte Carlo experiments that has been run with the policy or with the hybrid of optimizer heuristic.
That's true. So this after you train the policy, you get it back into AnyLogic and put it in the helper, set it up. Then run, I'm running the Monte Carlo. Because of the stochastic nature of this system, I'm running many iterations, 50 in this situation, in this case, to show how, in general, policies behaves compared to the baseline that we have. That's it for this example. Now Edward will continue for our AGV example. Thank you.
Thank you, Sahar. So now I'm going to go over the AGV example. So this is a simple AGV model in which the objective is to maximize throughput, which is represented by total finished products. To finish a product, each item must go through 3 stages. So there's product 1, product 2, product 3. They must proceed through these 3 stages, stage 1, stage 2, stage 3. And at each of these stages, one of these yellow raw materials is required to process this product. So an AGV will need to drop off the product, and then they'll need to drop off a raw material in order to proceed. The heuristic in this model is to simply select the machine with the shortest queue. And just as a side note, for some reason, the shortest queue heuristic is one of the hardest heuristics to beat. I have no idea why, but every time we encounter this heuristic, it's really hard to beat with RL. So that's the model. Now I'm going to go through the Pathmind helper setup. So this model contains 4 AGVs. So we set this as a parameter, but this is 4. So 4 AGVs controlled by an RL policy. So the number of controlled agents represents the number of agents controlled by Pathmind. And we called it control agents to differentiate between a reinforcement learning agent, so an agent controlled by the policy, versus a normal AnyLogic agent, which is not controlled by the policy. There's no right way to know whether or not to use multi-agent. Like you could also address this problem using a single agent or a single controlled agent, but we use multiple agents because it was beneficial for a policy to kind of understand the impact that each AGV is contributing to the system.
So is it fair to say that if I have a system and I know that there are components in it that might do things differently, or there are separate objects or entities in the system, it might benefit from a multi-agent scenario?
Yeah, exactly. So anytime where it's hard for a policy to see how the sum of its parts result in a certain outcome, it's probably better to separate each agent into separate controlled agents.
So basically, we provide more information to the AI that these are different things and know that as an additional information. Okay.
Exactly. It's less confusing for the policy. We separated observations into 6 categories. So the first one are observations around the AGV fleet, which you can see here. So it's basically the coordinates of each AGV, whether or not it's busy, its origin location, and the current station machine that it's at. So the second category is the home location. So whether or not the AGV is at home. So it's just one observation, so I'm not going to click in. Whether or not, so next is the observations for the source lines. So whether or not a product is ready for pickup. Observations around the inventory. So if I click into this function, you can see like the number of products currently in the feed, the number that is expected to arrive, and also whether or not pickup is even possible, right? So after that, we have observations around the product processing progress. So basically, at what stage the product has been processed so that the policy can be a little more proactive. And then time itself as observation. So for the metrics, we added a lot of different metrics, but we're only using a subset. So in Pathmind, you can add every KPI or metric that you care about for tracking purposes, but you can only use like 1 or 2 of them for the reward function. So I'll show you that in a second. So now looking at the action space, this is called a mixed tuple action space, which is a more advanced type of action space. We basically separated actions into 3 pieces. So the first is basically the source machines. So if I go to simulation, this would have 11 possible actions. If you look here, so 0, 1, 2, 3, 4. So these are 5 source actions. And then 0, 1, 2, 3, 4, 5. So these are 6 actions representing which machine to go to. So 11 in total right there. And these are actions that represents a pickup for an AGV. So the second type of action is a destination machine. So the destination machine represents any of these machines. So 0, 1, 2, 0, 1, 2. These are the destination machines for the AGVs to take the product or materials to. And then finally, an action that represents the stage. So 0, 1, 2. So stage 1, 2, or 3. So 3 actions there. And basically the policy will combine these actions together to tell the AGVs where to go throughout this production process. So I think it'll be a little more clear when we run the simulation. Finally, there's this thing called skip. So skip is a field that is unique to multiple agents, and it essentially skips an AGV that does not require an action at a given point in time. So for example, if an AGV is in transit, we do not want to trigger an action because triggering actions unnecessarily will confuse the policy. It makes learning very inefficient. And finally, for the trigger, instead of using the event trigger, we trigger it directly in the simulation using this query in action function. And basically, all we're really doing is we're triggering an action whenever an AGV is idle. So now that this is set up, you can export this simulation to Pathmind. So again, you go to RL experiment, you click export to Pathmind. Once exporting is done, you'll be prompted to write a reward function. So this is kind of like the same page I showed previously. And I essentially separate the rewards into good stuff and bad stuff, right? So the good stuff here is throughput, utilization, and essential deliveries. So we want to maximize these values. And you might notice that there's some like weights applied to these rewards. So the point of a weight is two things. So the first reason you would add a weight is to explain to the policy what's important and what's not important, right? And the second reason is you might want to normalize your rewards so that the policy would consider them equally. It's kind of more of an art to figure out what the correct weights are. A lot of these we kind of just guess and check, and then rerun experiments until we figure out what works and what doesn't. Now for the bad stuff. So these are punishments. So you know it's a punishment because there's a minus sign here. So like we're trying to minimize full queues, full conveyors, empty origins, and the trip duration, right? So once you specify your reward, you might also notice that the rewards that you define in Pathmind Helper are also shown here, right? And as well as your observations. One thing you can do with observations is you can toggle them on and off. So say like, maybe you're not sure if this observation is important or not, you can just turn it off and train the policy again. So you click train policy. I've done this already, so I'm skipping ahead. But once the policy is trained, you'll be presented with these charts. So I would guess there's two things that are interesting here. One is you can kind of trace the evolution of the policy over time, right? So you can see that it starts out pretty bad, but as it experiments and explores, it gets better and better, right? And I guess the second thing is you can also inspect all your other KPIs, right? So even the ones that you did not use in your reward function, for example, like delivery stage or something like that, you can take a look and see holistically how the policy had performed.
So, Edward, I have a question about this. So all these rows that I see for reward, and some of them are negative or positive as reward or punishment, are they all considered to shape the summation of the reward function, or are these considered as alternative reward functions?
Yeah, so these are considered cumulatively. So this reward variable, so throughput would add to it, so make it a more positive number. And then, for example, a longer trip duration would subtract from it, which is a bad thing. And after every time the policy takes an action, it will look at all 7 of these rewards cumulatively to decide whether or not they did a good job.
And you multiply them by some values to give them different weights, right?
Yeah, so two things to give it different weights, so they have like a relative measure of importance, and also to normalize the rewards so that the policy will consider them equally.
What is the reason that I want to have multiple experiments? What the benefit of having alternative experiments?
Yeah, so it's an iterative process to discover the best reward function. It takes a really long time. So one thing you can do with Pathmind is you can run multiple experiments with different reward functions in parallel. So, for example, I can potentially run 100 experiments at exactly the same time, all with different reward functions to quickly discover which reward function is the best.
Okay, so basically I can test all of my hypotheses in parallel, put all of those in the Pathmind web app, and come back later to see which one kind of perform better. Best.
Yeah, and just to emphasize, like typically, if you were to train locally, you can only do one experiment at a time, right? So if every experiment takes a day, 100 experiments will take 100 days, right? Like over 3 months. But in Pathmind, you can run 100 in parallel. You'll get 100 results within 1 day. So it's a lot more efficient.
And my last question is, Edward, how Pathmind decides that an experiment is done and it stops from running more episodes?
Yeah, so we have different criteria to stop the experiment. So one is the convergence criteria. So you see it says training has converged. And basically, if this reward does not change by more than 1% over a certain number of iterations, we will cut the training and assume that the policy has converged. And converge means it reached the best possible outcome. If it does not converge, we would cut off training at 500 iterations or 12 hours. But these thresholds depend on the type of plan you are on Pathmind. So for a professional user who's paying a subscription, they would get a lot more training. Okay, so the next step is to export the policy and validate the results. So once training is done, you click this export policy button to download the policy file, and then you go back into AnyLogic and change the multi-use policy and point it to the policy file. So there's typically 2 ways to validate a policy. So the first way is what Sahar showed. You run a Monte Carlo. So I've already run one. You can see here. And you basically compare the heuristic, so this is shortest queue heuristic, to the Pathmind policy. So as you can see here, with the Pathmind policy, the throughput is a lot higher, around 77, versus the heuristic which is 43. So the next question that you're probably wondering is how did the policy do better, right? So what you can do after the Monte Carlo is you can actually run the policy using your simulation. So I'll show you a comparison between the heuristic and the policy. So if I run this with the heuristic, speed this up a bit, you can see that products and supply are being dropped off to the machine with the shortest queue. So pretty straightforward. So whoever has the shortest queue the AGV would schedule a trip to them next. So it looks fine. There's not much backlog, not much build up on any of the machines. Now if I stop this and run the policy, it looks very different. So one thing you might notice that machines 3 and machine 7 are completely ignored. The policy does not use them. You can literally just get rid of these machines. It does not care. And the second is you might notice that these 2 AGVs, be clear if I speed this up, they're kind of tag teaming. Like one's dropping off product, one's dropping off supply, and then these 2 down here are kind of tag teaming at the bottom right corner. And the policy kind of figured out that if they just focus on the top left and the top right, the bottom right, it can reduce the travel time for the AGVs and thus improve the throughput a lot better than the heuristic. So that was kind of how the policy learned to outperform the shortest queue heuristic. And that's pretty much it for this model. So in conclusion, to sign up, go to pathmind.com. So if you go here, you can click sign up for free. And just to explain, as a free user, you get unlimited experiments, but you can only run them one at a time, right? So you'll need to upgrade to professional to run parallel experiments. As for tutorials, if you go to help.pathmind.com, click on this tutorials section here, and all our tutorials will be presented here. So you can try out any of them. Yes, and finally, if you go to AnyLogic Cloud and if you search Pathmind, you can kind of look at some of the tutorials that we created, as well as some that our users had created for inspiration, right? So that's where you can take a look. So in the next webinar, we're planning to show more real-life examples of reinforcement learning. So yeah, stay tuned.
Thank you, everybody, for joining us today. Thank you, Pathmind team, for helping us with recording this webinar. Sahar and Edward are with me today to answer your questions. Thanks to Tyler, we summarized some of your questions. There might be some questions that are not in the list that I'm going to ask. If that happens, we will answer those questions with a follow-up material that you will receive in the next few days, hopefully very soon. So Sahar and Edward, if you can hear me, I will go over the questions. Okay, cool. So some of these questions you already have addressed somehow during the webinar, but I think asking them again will clarify some of the questions that our audience had. The first question is there a free tier for using Pathmind?
Yeah, so we have a free student hobbyist plan. So it's limited to one experiment at a time. And you can export your models from AnyLogic to Pathmind using AnyLogic's RL experiment feature. So if you sign up, you'll see it available as an option.
Okay, great. Thank you so much. And I think there's a second question. I'm going to change the order of the questions that I can see in this list. It's kind of related to the same question, but from the AnyLogic side. What if I don't have access to AnyLogic Professional for exporting the model? Can I still use Pathmind and I add with PLE version of AnyLogic? So Edward, do you want to answer that question as well?
Yeah. Yeah, so PLE, you'll be able to export via RL experiment, but there's some limitations. Like for example, I think the on certain libraries, like the fluid library, for example, there's a limit to the runtime, like 1 hour. So we won't be able to fully train a policy in that case. But you should be able to apply Pathmind to basic models using PLE for free.
Exactly. To add to that, for people who have experience with AnyLogic, AnyLogic Professional license lets you to export models and use them and run them external to the AnyLogic development environment. But we added a feature to the PLE that lets you to export models exclusively just to for reinforcement learning, and the limitation that you get with the PLE or personal learning edition would be also applicable for those exported models. For educational purposes, for personal learning, that would be more than enough, and that PLE version actually is very generous in the features that it has with it. Okay. So, okay, that's another one that you briefly addressed, but and you demonstrated that how easy it is to use Pathmind. But the question is, what type of background should I have to be able to use Pathmind? Basically, I would add this to, I think this is my thing. Do I need any extra coding or any extra knowledge of or deeper knowledge of reinforcement learning before somebody can use or experiment with Pathmind?
Yeah, so Harwin probably know best, but you basically just need to have a good understanding of your simulation. You don't have to have any data science experience. We kind of automated everything in the background, so you don't have to worry about integration with some kind of framework, algorithm selection, hyperparameter tuning. We've already done that for you. So all you have to do is just focus on ensuring that your simulation reflects the real world, and then Pathmind will handle everything after that. So you don't have to have too much experience, but you do need to kind of be able to dissect why reinforcement learning perform better in certain cases, right?
Okay. And from my own experience, and Sahar could also comment on this, is from a simulation modeler perspective, you can focus to be more, do what we are more familiar with, building simulation models, and just make a little bit of change to it to make it RL ready, or make it in a way, or by just setting some setups in the Pathmind helper to help the connection happen with the Pathmind web app. So Sahar, I know that you have lots of experience with both AnyLogic and the Pathmind. Is there anything that, any suggestions for the new users, or anything that they should pay attention to?
Mm-hmm. Yeah, it was to cover that, but the most important is to know what observations are needed, how do action work, the sequence that you want to make the agent to by do action change the system, and then in the observation reflect that. So show the evolution of the system in the observations. Also, Pathmind is has some more advanced features like multi-agent. So we support multi-agent formulation of reinforcement learning, which we have docs that cover them, and also Pathmind offers technical support. If you have problems, you can reach out to us. We will help. And also some more advanced features like action masking we have added newly, and they are all documented in our tutorials. So yeah, give them a look. But you'll be fine. You don't need to learn any new language or know reinforcement learning yourself.
Okay, fantastic. And I can actually say that as well. If you looked at Edward at the end of the presentation, demonstrated how you can get access to those tutorials and resources in the Pathmind website. There are a comprehensive list of tutorials and examples that you can look into. And if you just wanted to see some examples and see the results, go to cloud.anylogic.com and search for Pathmind. You will see a large number of models that Pathmind team has developed with collaborators, and they are pretty interesting examples to showcase real applications of RL. So yeah, that was all the questions that you have. Any other final remarks, comments, Edward and Sahar, before we end the webinar?
No, I would just encourage everyone to sign up, and feel free to reach out to us, and we can, help you out and talk about different applications of reinforcement learning.
Okay, fantastic. Thank you again, everybody, for attending the webinar. As always, the entire webinar is the recording of this webinar, including this live Q&A session at the end, will be available on our YouTube channel very soon, and we will send you a follow-up email that has the link to that recording, and also answers to all the unanswered questions. If you have asked questions near the end, we probably didn't have a chance to compile them and ask them right now, but we will make sure to answer all the questions. You will also get a link to a short survey right after the end of the webinar. We really appreciate your feedback. It really helps us to improve these webinars in the future. And yeah, look for that follow-up email. Thank you again, and thank you, Pathmind team, for helping us with this webinar, and have a great rest of your week. Thank you.
Thank you.
Thank you.